Alright, time for another DraftPhysics.com, DebatePhysics.com also. Video presentation to a deaf and dumb world, but nothing I can do about that. I can only do my job, which is to make little basic logical arguments and say, come on, just concede the point, okay? At minimum, the science is incredibly undercooked. You haven't really proved any of what you're claiming to be the truth. All the way from the Big Bang to entanglement to expansion to energy to gravity. You've made a mess of it all because you've jumped to conclusions and you haven't been scientific. It's just that clear. Really don't care about doing science. You're just doing a bunch of grandiose imagining. Yeah, and forcing it to fit, even though the evidence does indicate it's nonsense. So you just keep arguing this kinetic energy thing, and you're just saying, come on. It grotesquely fails the lever test. The lever tells you what equals what. So, I mean, how many times do I have to describe it? But, I mean, the simple truth is you can put the bullet at one end and the recoiling gun at the appropriate place on the other end, and you can create an oscillator that would work just fine because it's the same energy, just in a different form of mass and velocity. But it's always just mass and velocity. That equals your capacity to weigh something. And weight is pressure. Weight is the capacity to give something motion. Okay. So this, whatever, bobbly boo. Imagine catching a falling bowling ball. How I catch the ball have anything to do with how much energy the ball has? And the simple point is again, you have zero evidence that if I change the mass to velocity, that is, I make the ball really light going very fast, or I make it heavier and going much slower, that I in any way change how many pins it'll knock down. Because I won't. Because the only thing the ball has as energy that it can transfer is momentum. It can't transfer whatever kinetic energy is, okay? Your imaginary energy can't be transferred. So it's meaningless. All right. In case A, you catch it slowly by decelerating it over some distance like 30 inches. In case B, second, doesn't matter. Okay, in case, how is that measuring its energy? Oh, yeah, right, it isn't. Case B, you catch it by stopping it almost immediately when it hits your hands. Don't you agree that you have to apply a much larger force? So again, the amount of force is just another word for momentum, as Newton pointed out. Force is just momentum. The force can hit you quickly, the force can hit you slowly, and it has a mass, and that's it. How much mass does the force have? How much velocity does the force have? How many photons are hitting you, so to speak? At what frequency? You could even argue. Or, let's see, there's probably other examples. Wind, lots of things. Okay, it's just about a mass and a velocity, and that's it. So whatever you're calling a force, I don't know. What do you think force is? Some magical substance? All right, a much larger force over a very short period of time in case B. Yes. You're applying all of the force in a shorter period of time. The net force, okay, will be applied over a shorter period of time. So what? That doesn't mean you applied more force. It just means you applied it over a shorter period of time. Therefore, the matter that was receiving the force didn't have time to absorb the force, and it broke. So what did you prove? You didn't prove it has more energy. You just proved that, yes, applying the energy faster means I can break things. And that's what every single experiment shows, and nothing more. Okay. So again, you just stick to tug of wars. Again, prove to me that your 8-pound bowling ball going 16 miles an hour, hits the side of I make a U-shaped piece of metal and I shoot 2 bowling balls out, right? They hit it at the same, and I have it so they'll hit at the same time. Even though one has twice the velocity, I put it twice the distance. They hit the surface at exactly the same time. The 8-pound ball isn't going to move it anywhere. It's not going to win the tug of war, proving it doesn't have more energy. All right, for a short moment, the ball would feel much heavier, right? So again, this feeling thing is really idiotic. The fact is it's going to apply the same capacity to move something, the same pressure. And you can apply the pressure over a short period of time, you apply the pressure over a long period of time. It's the same amount of pressure. One atom going 1,000 miles an hour, same thing as 1,000 atoms going 1 mile an hour. They'll do the same pushing in the universe. They'll engage with other material objects and create the same MV, because that's all they have to exchange is their MV. They can't exchange that squared crap. A more extreme case would be one where you don't just stop the ball from falling but hit it back up like a volleyball. So again, more nonsense. So this is the case like I could throw a balloon at a car coming towards me, a beach ball. And the beach ball will come back to me with more velocity than I threw it with. Well, because, yes, it took some of the car's velocity. Not complicated. All right, even larger force would be needed, don't you think? Some more baby talk. What are you talking about? I mean, literally, what are you talking about? I mean, of course, if you're going to get more energy out of something, you have to put more force in. You're the idiots who think I can put 100 momentum in this way, hit a mass that's 3 times this mass, and now I have 133 going that way. You're the one who thinks you can create free momentum. Not me. You. Loony. Kook. Where'd you get the extra force from? All right, this is exactly what happened in the ball dropping experiment. So this ball dropping experiment, I've already spent 3 videos on. I'm not going to waste any more time. If you bring it up again, I'll just block you. This is nonsense. This is a waste of time. Okay, there's no way a 44-gram ball dropped 15 centimeters could weigh 23 newtons, 32 newtons. It can't happen, moron. You're a moron if you think. I mean, it's just moronic. All right. The measured force was very large for a short period of time. So again, this is just baby talk. It cannot create. A Newton is not some kind of variable force, It's a specific amount of pressure. All right. So 32 newtons comes out to 32 sticks of butter. Okay. The weight of 32 sticks of butter. Do you understand? It's a real weight. Right? And it can't weigh more for just a little period of time. And we'll just say the average amount of weight is how much force it had. That's not how it works. Okay, because the ball changed its motion so suddenly. Irrelevant. I don't know. What can you say to these people? It's really just no point. And the values were what would theoretically expect with a bounce like that. So the measured force was very large for a short period of time. It was as large as it was for all the other periods of time. And you took the average of those readings, you'd still end up with a number that's way too high. The ball changed its motion so suddenly. And the values were what would be theoretically expected with a bounce like that. So again, the bounce wasn't all, it's, whatever, 6/100ths of a second, was the total time. And, it's got its curved line. But the point is it can't create a peak weight that isn't registratable as a weight, an actual weight. So it can't achieve a pressure that high, or it would compress a spring to that amount. So it's just nonsense. All right. Weight is a real thing. You can't undo your weight. Let's see how else to say that. Well, no need. So I think it's a pointless argument, okay, to sit there and argue that, like I said, even if you took the area under the curve, the average, it's still 15, which is way too high. Because the truth is it has to be something like 3. All right. So enough of that. So that's it for the comments. Just kind of a waste of time. But I mean, it's, there's no point. They're never going to deal with my arguments. And so if you're not going to deal with my arguments, like, why should I bother with you people? I mean, why shouldn't I just insta-block you if you're not ever going to argue what I've argued in the videos? That is, you have zero evidence. All right. Now, you're going to say in 350 years, you can't come up with one single experiment where you spin something 5 times as fast or you push something 5 times as fast and show that it took 25 times the force to do it and it produces 25 times the work. You'd think you'd have that experiment somewhere by now, right? I mean, if it was really science, you'd think, oh, yeah, they'd have that covered. And they might even cover the 10 to 1 difference, right? So, 10 times faster is 100 times the work. You'd have some example somewhere. You have nothing. And again, I made the lever argument, the water argument, the gear argument, all these arguments, and if you ignore it, every single one of them, to just keep rambling on about some mysterious way that somehow if I change how much time I collect the force in, that somehow it's less or more force. I can't change how much force something has by catching it slower or catching it faster. It doesn't change how much force it has. It'll certainly change how much damage I do to the collector. But it's not going to change how much real energy it has. God damn it. Alright, so I'll do a little bit of draft stuff. Just stuff I've been thinking about. Always thinking about the subject of the electron and the fact that there's no real good evidence you can move electrons in a vacuum any kind of real distance. So there's no evidence that there's 2 satellites in space, a few miles apart, and they send a stream of electrons from one satellite to the other satellite. All right, so no evidence that electrons are flying from the sun and hitting the earth, or electrons are coming from space at high velocity and hitting the atmosphere. So they have no evidence that elementary particles, electrons or protons, can do this, move through space. All right, and that I would argue that atoms can, because they have a nucleus, and the nucleus is the key. The hydrogen helium nucleus can overcome the problem of drag. So the truth is, in real space, electrons and protons are dragged to a halt because they interact directly with the force. And it's only by taking advantage of the fact that when you are moving in one direction, you're getting hit by less energy in the other directions, technically, in the same at any one point, okay? Because in a sense, you're evading the equality. You have more hitting you from one end than you do from the 2 sides, therefore changing the relationship of the shape of the helium nucleus, and therefore creating a mechanism to fight against the drag. So for every bit of drag you're running into, you're compressed your atom, and that compensates for the energy lost by pushing the electrons closer together. Anyway, so let's just play with this idea a little bit. So there's so many ways they create the electron gun idea. So they take a vacuum, all right, and the idea is the vacuum is supposed to be an insulator. Okay, you can't move electricity through a vacuum. All right, because you need atoms. So the catch is that in a vacuum, there's no atoms to create a pathway for the transfer of the charge. So discharges like lightning are being created by a bunch of atoms that are ionizing as the lightning bolt goes through. It basically changes the shape of a bunch of atoms and creates a bunch of light, okay, and gets the electrons from one place to another place by a chain of ions. All right, atoms. It uses atoms to transmit the electricity. So the electricity isn't really moving from one place to another. It's going through a conductor. It's making out of kind of a crappy conductor out of what's in the atmosphere. And, they've done all kinds of experiments, put little tiny copper wires up with balloons, and it does the same thing. It just, the lightning hits the balloon, then vaporizes the little tiny wire, and all the atoms around it using a plasma. So that's the other way they can do it, is they have an anode and a cathode, and they put a high voltage across it, and then shoot electrons through a gas, and then you get light again. So that's like neon lights, all of that stuff. So again, it's a high voltage and a potential across, and all the same rules. And then theoretically, okay, so if you take the gas out, you don't get any light because there aren't any atoms. And the best you can do is that there'll be a little glow at the anode, because you're going to basically just pull atoms off of the surface and create a little tiny bit of plasma. And that'll be it. That's all you're going to get out of it. So you're going to just basically use the atoms of the material by throwing them off, and use them, okay, as your conductor. And so over time, obviously the anode would deteriorate and fall apart, and you're pulling atoms off of it all the time, and you'd end up depositing stuff on the cathode, which actually does happen. So you can actually, in a way, tin something or plate it by using electricity. Take atoms from one material and literally throw them at another material and have them stick. So clearly atoms can be moved from one place to another place, okay, and probably can be moved substantially large distances once you give them a velocity, because they're not going to be dragged to a halt. And so that's the interesting part. So how do you know, when you create one of these systems, what you're actually getting? Now, another experiment they do is this little gold leaf one, where you can put a negative charge on a plate, and then they'll shine light on it and knock electrons off and reduce the charge. Now that's interesting, but what I haven't seen them do is take the neutral plate, okay, with no charge on it, all right, and then bombard it and see if you can make a negative charge. Because you would think, applying pressure to the surface, you're going to push the electrons into the surface, and that's going to increase the pressure, the voltage of the surface, in the sense that the electrons will be under a higher pressure. So even though you didn't add electrons, you can find the space that the electrons are in, which I would argue is the same thing as increasing the voltage, the pressure between the electrons. So you would think they would rebound. Now, there are materials, right? The phosphorescent type materials where you can shine the light on it, and then, for whatever, 10 minutes after you shine the light on it, it's still radiating the photons, the extra energy you put into it. So you shine the light goes in, pushes in, creates pressure inside, voltage if you want to say it, and then the voltage leaks out over time as visible photons. If the photons of a different color than the ones you put in, generally speaking, of a lower energy than the photons you use to energize the surface. Now this is also how they sort of make X-rays, is a similar kind of process where they use layers of stuff and create the necessary energy, and then use a separation between two materials, and then use one material that actually creates the X-rays. So there's so many interesting little stages to this in terms of figuring out what you're actually moving, what you're actually sending from one place to another. Are you sending force? Are you sending electrons? Or are you sending ionized atoms, which carry a charge, obviously? Now, the trick is you couldn't you can't really imagine conveying a whole bunch of electricity through sparky type discharges that you're creating out of the material itself. So you're heating a material, creating a bunch of atoms flying off, and then saying, how much can you do that without the material dissipating and, finally using it up? So you couldn't create too much movement of electricity if you're actually firing ions. But again, there is the counter argument. Now, things like halogen light bulbs sort of take advantage of that because they run really hot and in a vacuum, and then theoretically they're disposing, a bunch of atoms are flying off of the filament because of the heat, but they're bouncing back onto the filament because they don't stick to the glass because of the heat, which is interesting. And they're so hot, that you can't touch them, because if you leave any oil on the surface, it breaks the glass because of the uneven heating the oil on the surface will create, which is also interesting. So there's a lot of subject here, so I will speculate some. Right, there's just so many experiments. So that's why this gets a little bit difficult, is there's so many experiments to consider. So they have also the one where you drop little bits of, say, even styrofoam or oil or whatever, and you expose them to X-rays, okay? And you basically can change the charge, the net charge of the object. So the explanation would be is that the X-rays are hitting the surface, and there's a 50-50 chance that they end up knocking a positive ion or a negative ion. That is, it breaks off of an atom. The atom either takes the extra electron with it, or at least the extra electron behind, the binding electron. So the binding electron has a 50-50 chance of either going with the atom that leaves are staying, okay? And so that's also very interesting. Now, I was talking about the leaf experiment. Now, I haven't seen this done in a vacuum, so that's interesting. It's still a little bit short. Anyway, I haven't seen it done in a vacuum, and you would argue, see, the electrons, and my argument is going to be, is the electrons don't have anywhere to go. So, I mean, if you disrupt them off the surface a little bit, where are they going to go? They got nowhere to go. So what you're really doing, when you're shining light and it's charged negatively, so it has an excess of electrons, is you're really just saying that all the atoms that are hitting it, the atmospheric atoms, you're just saying that you've put some energy into the metal, and it's just basically saying take away the electrons. So you're really just creating a bunch of negative ions. It's really the wrong way to say it, right? Negative ion has the extra electron. But anyway, it's sort of backwards. And the positive ion is lacking an electron, left one behind. So anyway, you create a bunch of these atoms that have the extra electrons. So I guess I could just draw that as a circle and a dot. It has the extra electron. So it's taking the electrons off the surface because you're using the atmospheric atoms to carry the electrons away, because electrons really aren't going anywhere. I mean, if you push an electron off of a surface, there needs to be another surface for it to go to, or it's just going to say, I'm going where there's protons. I mean, the electron's always just looking for a proton to head towards, in a sense. The less crowded and less crowded, so it has to have less electrons. Well, it has to have less net charge, right? Period. So there has to be more positive than there is negative in a location for an electron to head that way. And then when it arrives, it finds out, oh, there's a bunch of electrons on the outside. They're stronger because they're closer to me. So that's the catch. I mean, these are all really important little details, and it's unfortunate that physicists don't really talk about any of this, I think, very interesting stuff. So you have the positive nucleus, and then you have these electrons on the outside. So you can sort of understand that from a distance, the electron is seeing the positive. And when it gets up close, things get different. Because it starts getting, see, from a distance, this distance and this distance aren't very different. Okay? But when it gets close, this distance and this distance is a big difference. So from a distance, the electrons and the proton are very close to each other. But as it gets closer, the electrons are twice as close to it as the proton is. So as it starts getting the diameter of the atom, when it starts getting within the range of 3 or 4 atoms, now it's seeing the electrons as being really strong, and the proton isn't as stronger, as it was from a distance. And so all of a sudden, something that seemed attractive now becomes repulsive, and it's stuck, staying out there. So it's still attracted to the proton, but there's a balancing force coming from the other electrons, so it can't get any closer. So that's why the electrons hang out on the outside of the atom, is because they can't get to the barrier of electrons, which is, I think, really important to understand. All right, so we'll see. There's a couple other experiments I want to go over. All right, so back to the gold leaf experiment. So my assertion, I guess this pen has about had it. All right, so the idea would be is that if you did it in a vacuum, okay, and then you shine the light on it, would it be possible to create the negative charge? That is, start off with no charge or a positive charge and take away the positive charge, which I haven't seen them do, in the sense that add directly by adding energy, increase the voltage with the light. So a direct creation of voltage, that is pressure, electron pressure. So it's not, voltage isn't about how many electrons there are. Voltage is about how much pressure is between the electrons. And so the argument is the more of this pressure you push on any surface, you're basically just pushing pressure on electrons, and they have to equalize that pressure. Now that's the question, is whether they just equalize the pressure, but they have to equalize the pressure on the surface, so it always ends up on the surface, and there'll always be a higher density of electrons on the surface if you increase the pressure, I would argue. So theoretically, instead of increasing, instead of taking away the electrons using light, you should be able to just increase the voltage, the negative voltage, right? By just shining light on the metal in a vacuum. So that's the experiment I haven't seen. So that would be helpful. But again, they haven't done any. There's just so few experiments that they have done, and the ones they have done, they've done 5 million times, and they just don't tell you enough. And there's all these undone experiments that I think would add a lot more insight, like spinning a motor 5 times as fast and seeing if it uses up 25 times the electricity. Yeah, they haven't done that one. Alright, so I'll go over a couple of the things that I say would have something to do with this subject. Alright. And so you sort of have to understand that the proton and electron are producing a different force. So when you have something that's net positive, all right, it's radiating a force the electron can't see. So in a way, you could understand it that the normal field would have a force in it that the electrons would be repelled by. But because you have a proton here, that force has all been converted into a force that the electrons can't see. So in a sense, you have a weaker field. So the electron is going to go into a field that doesn't contain, the same density of the stuff that's going to reflect off of it or bounce off of it. So it has an easy path to a positive. Something with a net positive is creating a field that's more red than blue. And so there's less for the blue thing to reflect off of, to bounce into, because the red just goes through the electron. All right. So the idea would be is that you take a surface and you heat it, or you do something else to it, and then put a voltage into it, and you can liberate these electrons. That's what they're claiming. And I'd argue if they're doing that, the electron is being liberated with a bunch of energy quanta that's going to push it. And so this is essentially like a cosmic ray or something. I mean, it's probably the highest energy you can create is the energy pushing an electron. And it just depends on how fast the electron is going. The faster it's going, it means it collected more of these little bits to go faster. So there's a whole bunch of them. But what's going to happen when it plows into the field, there's going to be some blue bits in the field. And this electron is going to reflect each one of those, okay, at a different location. And the fact is, the faster it's going, right, the more compressed that frequency of what is going to reflect off it will be. So if it's going really fast, then it'll make these things really tight, because it's going to go across this space in a very short amount of time. It's going to hit each one of those things and create a reflection, and it's basically just compressing it. Just as my hand, if I could move my hand the speed of light, it would collect all the photons that are reflecting. So the ones here, the ones here, the ones here, the ones here, all of them. And if I stop my hand instantly, then all the photons that hit it in this whole period would fly off my hand at once. So I'd have a zero frequency. I mean, yeah, an infinitely high frequency, however you want to put it. A very high frequency. They'd be very compact. And so the trick is that if electrons are flying into this higher density, in the sense that they're going to hit more stuff going forward because they're going into the field fast, all right, and so they're going to hit more going this way, and they're going to have less pushing them. So there'll be a little less pushing them because they're going as fast as the pushers. Essentially, the pushers can't reach them. It can't get pushed, so all it can get is slowed down. But the trick is that to get slowed down, it's going to lose its energy, okay, in this direction, and it's going to reflect the energy in that direction. So in a sense, it's going to create a lower frequency photon forward, because each one of these bits they'll be increased in the frequency. They're coming this way, essentially, right? They're not, let's say they're not even moving, but they of course always have to be moving, but they're in space. This thing's going to plow into those things in space, and the idea is that they're going to have to reflect. Now, the trick is the sideways motion. I don't think I'll get into that in this argument. But obviously it's sort of a tricky statement about whether a bit of energy can be going this way and this plows into it as it goes across. I don't think that's a possibility. So the sideways stuff can only hit it by hitting the actual object, and that's the catch. So when the object's moving fast, it's less likely to be hit. So there's less energy hitting this way and more energy hitting this way. And somehow that works for atoms, but it doesn't work for electrons and protons. So the idea would be is that the electron would eventually stop because it's going to plow into more force and lose all of these little bits are going to fly off. So it's not going to have any energy pushing it decidedly in one direction or the other direction. And it's just going to be stuck in space looking for a hint of a place where it's more positive again. So someplace there'll be and it'll drift in that direction, theoretically. But the force that was pushing it is still there. It's just been diminished in the sense that you have a high frequency X-ray or a gamma ray or something like that. So this sort of happens in accelerators. So accelerators produce, theoretically, electrons and they keep increasing their velocity, they have to keep pushing them. It's just a fact. And so they keep adding energy to the electrons to keep them going. And the idea is by the time they hit the target, though, they've got a bunch of other stuff moving with them, a bunch of X-rays and gamma rays and other radiation. So there's a bunch of radiation in the form of gamma radiation. And that sort of has to be explained. Why is it so much of that? And I guess the argument I would make is there's so much of that because the electrons can't travel the distance, but the force can. It's just going to be a little diminished by the time it gets there. And it's hard to call an X-ray a diminishment, but compared to, infinite frequency, right? I'm just using that as a general term. The greatest frequency you can have is the frequency pushing an electron. So if there's more than one bit pushing an electron, it has a very small frequency. The two bits can hit almost at the same time and both reflect. So it's they're almost in the same, they're right next to each other in space. So it's the closest two things can be, two force bits can be, is when they're pushing an electron or proton. So anything lower than that frequency seems really high to us, like a gamma ray or an X-ray. But from it's still an expansion of the frequency, and so each time you would convey between electrons, even if the gamma ray hit another electron and pushed it for a while, the next time it loses the energy, it's going to lose it into ultraviolet or some bigger frequency, and eventually visible light, and eventually infrared. So it would keep getting diminished based on the fact that it can't hit a stream coming at it that's going to equal the stream behind it. So the force pushing it has an infinite frequency. A zero frequency, I guess you could say. Right? Well, zero implies no frequency, so that's no good. But anyway, yes. So you can just say it's got a higher Planck wavelength. Okay, a lower Planck wavelength and a higher Planck frequency, and it can only get smaller as you transition it, because nothing else could hit it with the same frequency except another electron, in theory. All right, anyway, so I'll pause and see if there's anything. So I'm just saying I haven't reached any hard conclusions. I'm just saying there's a ton of experiments, and they all have variables, and it's like doesn't get very fleshed out in terms of being able to draw any conclusions about what's actually in a system that we're looking at. It's like when they put electrons in a Helmholtz coil and get them to move in a circle. The only way we can see them is they have to put a gas inside the vessel. All right, so the compromise there is well, if the electrons are causing the gas atoms to ionize, then all you're doing is showing that the gas ions create a circle. You're not showing that the electrons are actually moving in a circle. So, it's those kind of little subtleties that are kind of important. So all you're doing is changing the shape of the conductor that's allowing the electrons to move from atom to atom. But because they're ionizing the atoms are being affected by the magnetic field, and so the atoms are lining up in a circle, and the electrons are just moving through that conductor. So, it's it's not a fake subject, and like I said, none of this is explored. They draw their conclusion, and they say, okay, this is what it's about, and they really don't speculate about how they might be wrong in the conclusions they've drawn, and that's not very good science. All right, back. So I thought what the hell? I'll talk a little bit about Stern Gerlach because, it needs its own video. I really do have to, really pick at it a little harder. But anyway, basic idea is that they take cesium, I guess they're using instead of silver now, the modern version. They heat it, and then they heat the vapor created. So it creates a vapor, then they heat the vapor also, and then they create a little hole, and so they're basically just shooting vapor, okay? All right. And the idea is they put it in what they call an even or uneven magnetic field. So they create a magnetic field that looks something like this. Okay. So the idea is that there's clearly a polarity, like a minus and a plus, okay, or a north south, make it more magnetic. They're actually using coils to induce magnetism into the metal. So the magnetism is induced magnetism. So they have a coil on the outside of the experiment, here and here, creating the north and south, and then they create a field. So anyway, the idea is that it's still a north-south field, but the difference is when you get closer to the south, you're not going to move towards it faster because of this curve. It's like being in this hollow sphere, and no matter where you move, the field is the same. So in this case, the field is the same, but it's still decidedly north-south. It's just that when you get closer to the south, you don't go faster. So it just has a consistent amount of pull in both directions. So it gets rid of the inverse square law, essentially. So it's not like you've made a nothing magnetic field. You've just changed the magnetic field so it's even. So there's not some strong pull one way and a strong pull the other way. The closer you get, the more you're pulled. The closer you get, the more you're pulled. So the idea is you can send this beam in that's going to be wider than your magnetic field difference would be. And the idea is each atom that goes in will be subjected to the same amount. So even though there's a north here and a south here, this atom won't be in more of a stronger field than this atom. So they're all being affected by the same amount of field, but they're still a field. They're still decidedly a north side and a south side, and if you just let it fly, it'll go one way or the other, okay? It'll still move in the field. So you're just changing how much it accelerates in the field. So it only accelerates at a constantly, at the same rate. It never gains more velocity than the amount of time it's moved in the field, I guess. Yeah, because you can't change. It's just always 9.8. It never, like with a real magnetic field, say if there was a 9.8 pull towards the north, as you get closer and closer, it gets stronger and stronger. And by the time you're right next to the north side, you got 1,000 times more, it's 1,000 meters per second, instead of 9.8 kind of idea. So they're just taking the fact that that the atoms will now be subjected, all of the atoms will be subjected to the same amount of pressure, no matter what their position in the field. All right. So I just took me a while to figure out what the hell they were talking about. So another thing they do in the experiment, right, is they spin a compass needle. And it's a compass needle with a very good bearing. I mean, it's very little, friction in it because will just keep spinning. Once they spin it, it'll just keep spinning. And they find that it oscillates, okay, in the field for quite a while. And that's just because you put momentum into it, and it's a pendulum. And as it swings in both directions, it's got the same amount of pull pulling it back, so it's almost an inverse pendulum. I mean, you just have to, turn it upside down to look at it and think of it, and you get the idea that it's like a pendulum. The force of gravity is what's really, and in this case, the force of the magnetism is just duplicating the force of gravity. So when you put the north pole, it will oscillate because you still have energy in it and has to dissipate the energy. And it can't dissipate it except through the bearing. So if it has a very good bearing, it's going to take it a while to dissipate the energy. So they make it, they're sort of implying that this motion happens from the field. And no, the motion happened because you spun the compass. If you didn't spin the compass, there would be no pendulum. There'd be no energy. There'd be no swinging. So, it's all little, I mean, you hate to say the word deceptions, but, they're kind of deceptions. So anyway, all right, so the beam is these atoms going through the north-south field. And so it's a real north and a real south. And as I pointed out, it just means that it's not stronger here and weaker here or any of that kind of crap. Distance doesn't matter from the north and the south. It's the same thing. And the simple idea is that the atoms are little magnets. Okay, so, and the very point is that all atoms, like most of the atoms in the periodic table, are magnetic as single atoms. Right? It's only when they become substances that the polarity is all mixed and they're not magnetic anymore. So they end up, when they join with each other, they join in non-coherent ways. Okay, so they end up destroying any magnetism they have. But the atoms themselves are polar and magnetic. So that's another interesting fact. Is that you don't have to, it's not just iron and nickel and cobalt and neodymium. Anyway, all right, so the experiment basically is you take these atoms, and the atoms have various velocities. So there's no, the velocities are, who knows. One of them could go very slow, one of them can be going extremely fast, because it's being created by heat and vapor and pressure, so you don't know what you're going to get coming out. Okay, all kinds of different speeds of atom are coming out, and the idea is they have a heated, maybe it's not cesium, maybe it is cesium. Well, anyway, then the idea is this coil, this heated coil, when one of these atoms hits the coil, it negatively ions, and now it can be attracted to a plate that will detect that. So they just move this detector back and forth across the field to measure the intensity, okay, of what the beam has done. And the question is how many of the atoms will be deflected? And that's the pattern they're going to detect, is deflections. So we're just taking all these atoms and we're going to just see if the beam spreads. And so the data basically, they it's unfortunate they don't really show it very well, but this is the idea. The chart will show that is the beam, okay, without the magnetic field. And as you start to apply the magnetic field, it does the logical thing at first, and it just spreads out. All right, and then it does this. Too bad I don't have another color. Well, maybe I do. I know I have a black here somewhere. I know it was here. I could always use this one, I suppose. I'll see if that works. See if we can tell the difference. It should come out white, I guess. All right, and what it eventually does is this. Okay, so yeah, that's visible enough. All right. So as you increase the field, first you create some spreading, which is natural, and then eventually you create spreading that equals, a complete division and nothing in the center anymore. And the simple argument is that the variable here, the variable of the speed, is what's really creating this. And what you're basically saying is, if I throw a magnet through a magnetic field really quickly, let's say the magnet isn't in the right orientation. So it's going through a magnetic field, and it's a little bit shaped like this. Okay, so it's a little tilted north and south. But it's going, the faster it's going, the less time it's going to have to turn all the way and move. Right? So you can understand that depending on how fast it's going will decide how much it can turn, because if it doesn't turn to the field, it can't move in the field's direction. It's still equal. So if it's going through straight this way, if it doesn't turn, it's got an equal amount of attraction this way and an equal amount that way. And it's only the more it turns that it can create the uneven, the attraction from both ends All right, and that's when it has less pull. So the more, it has to be in this or this. It can't be this or this. Okay, because then it's not going anywhere. All right, it's not going anywhere fast anyway. But it really has to do this turning. So you're going to understand the faster it's going, the less likely it is to turn. So that's why you have to keep increasing the strength of the field to finally get all the fast ones that aren't turning. And you have to put so much magnetic field that you force them to turn. All right. Even though they're going very fast through the field, you've increased the field enough to get them to turn. So the basic idea is, look, all you're really saying is that I made half the magnets went in this way, half the magnets went in this way. And all I did was show that's how I can move them. So this has nothing to do with electron spin. So they say this experiment proves something about an electron spin, when all you're saying is that obviously I can move them if they're going through the field, and they have a bias to create more motion. Then they'll move in that direction, and that's all you're really establishing. And the stronger the field, the more you'll bend them, and you can't bend very fast ones with a weak field. And that's sort of all it's really showing, frankly. I don't see anything else there. I mean, it's not. So the thing that would be good is if they would just vary the magnetic field more gracefully, so you can see this transition between this symmetrical lump and the idea of everything going one way or the other. And so it's just that there's a point where the field strength is strong enough that no matter how fast it's going, it flips. So you're really just saying, what's the flipping point? What's the strength of the field where every single atom, no matter how fast it's going, flips? So I think that's all that's in this experiment, frankly. And it doesn't show anything about anything called an electron spin. Just has to do with the atoms, and they are atoms. They're not ions. They're not, that's the whole point of using non-ionized materials that don't ionize easily, I suppose. So I don't know why silver and cesium would be good choices, but I think it's because they don't readily create ions, but I'm not sure of that. But that's just my guess. And the point would be is that even if it did create positive and negative ions, okay, and that's why they're polar, it would just ignore the positive ones. They'd just reflect off the detector anyway, and so it wouldn't change much in terms of. I should be back. So, crash computer. It's been a while, so I can't complain, I guess. Sort of related, which I've found a relationship. I have a whole bunch of tabs open in Firefox, and if I go to the National Weather Service weather site, their radar map, it's whatever. It's high tech, high bandwidth anyway. Radar picture. So if I do that, not go to the little GIF graphic, which is safer. Anyway, it does tend to blow things up, and even other programs. So anyway, just something I've noticed. It's just kind of curious that whatever the code is in that page, of all the pages I visit, it's the only one that creates this. Oh yeah, the system's going to crash any moment now. Kind of problem. It really doesn't. Half the time it doesn't crash. The other, it's a 50-50 kind of thing, or 30-70. Who knows? Anyway, so I did do that today. I did make the mistake of looking at the regular. I just did it by accident, but that was probably what caused the crash. Funny as it is. Anyway, so there was a whole bunch of stuff I did go over. So we were at Stern Gerlach, and I was just pointing out that this experiment really isn't about electron spinning. Okay, electron spin is not going to move the whole atoms and all of that crap, so it's really stretching reasonableness to be speculating that this is about the spin of an electron, let alone the orbit of an electron. So that got me on the subject of orbits, and me pointing out that this is another one of those perfect moments in my education where I said, oh, these people are nuts. They're just plain crazy. They don't know what they're talking about. It can't be. Okay, the description of reality is just so far removed from anything I could understand. So anyway, photons doing all this jittery stuff, yeah, that was garbage. And I knew this argument about how atoms combine and the fact that they share an electron, and sharing an electron means they do this wacky orbiting crap, this figure eight garbage, and that the electrons are spinning around the outside of the atom at 400,000 meters per second or some outrageous number, and that somehow, when the electron is way over here, somehow this nucleus stays here anyway. It just says, okay, I'm not going anywhere. I'll wait for you to come back. And it's all this, they had already taught me, okay, that orbits had to be really specific in terms of distance and speed. The distance dictates exactly what speed you need to stay in an orbit. And it would just be so complicated, this transition point. How would the speed be regulated? Because you'd end up going faster and you'd end up just shooting off, and it's not going to work. You don't see anything in space doing that. Okay, so that doesn't happen. It's bullshit. It's just really unlikely that you could have this perfect speed maintained and everything just stays and everything's so stable, because any irregularity, any movement of this nucleus would screw the whole thing up. It'd go all wacky. It just didn't make any sense. And it made so much sense to just understand it magnetically, as these are south poles and the electrons are little north poles. And, it made perfectly good sense that the electrons are stuck in a position, okay? And that's all you're doing. You're sharing an electron in a position. And the atoms are balanced. The electrons have this equidistant thing happening. There's the same amount of pressure. Clearly the electron wants to go to the proton, but the electron pressure is keeping it from going there, so that's all understandable. The idea of sharing an electron, or sharing two electrons, made perfectly good sense that the atom could do that, and that they'd be in real positions. And then I could, I can bend it all I want, I could flex it, I could do all kinds of things to it, and it's not going to break. And so why would I believe that electrons are orbiting? Because Bohr said so, in 1920 whatever, 5, and now everybody has to believe it. And it's just like, well, what did he base it on? Just guesses. Oh, it looks like a solar system. It's like moons and things and planets. And no, it's not. It's nothing like. Because it's not gravity that's controlling it in the first place. It's charge. So it's not the same thing. And like I said, the magnetic model works so well. Why would I mess with the charge model of the atom? And, all this nonsense of electrons with all this momentum just doesn't make any sense. And then on top of that, they're saying the electron is doing something called a spin, whatever the hell that could possibly be. So in spite of going around, it's also spinning. Yeah, no, bullshit. So anyway, just saying, since I was 10 years old, they haven't shown me any evidence indicating I have any reason to believe electrons are spinning around nucleuses. No good reason to believe it. And it makes so much more sense that they're not, because it explains why they're so durable. Allergies. So anyway, we'll call that a video and see if this recorded and such. So anyway, I did talk about something else in between transitioning, but anyway, it doesn't matter. So till the next time and such and so forth and whatnot.